Today's speaker, Dr. Babak Mahmoudi. Dr. Mahmoudi completed his undergraduate training in electrical engineering and artificial intelligence. He transitioned to biomedical engineering for his PhD at the University of Florida, where he developed a framework for designing intelligent neural interface control systems using reinforcement learning to enable automatically decoding of brain signals via closed-loop interaction with the nervous system. Currently, he is an assistant professor in the biomedical informatics and biomedical engineering program at Emory and Georgia Tech, and he's also the director of the neuroinformatics and intelligent systems lab at Emory. Currently, his research is centered at the interface between artificial intelligence and neuroscience, and he's leading multiple collaborative projects in this domain on the design, development, and implementation of various AI platforms for neural decoding and closed-loop modulation. Applications include memory, movement disorders, epilepsy, and psychiatric disorders. I'm personally very excited for his talk today, and I'm sure many of you are. So I will give Dr. Mahmoudi the floor.
Thank you for the introduction, and thank you for the opportunity for me to talk about some of the works that we are doing in the area of AI and closed-loop neuromodulation. Good morning, everyone. So today I am going to talk about closed-loop neuromodulation from an AI standpoint. I will cover certain areas in this domain. I will talk about the AI for closed-loop neuromodulation as a new paradigm. I will also talk about some system design elements for biomarker discovery and automated control and closed-loop optimization. And I will also talk about platforms for design and implementation of such systems in clinical and experimental systems. Neuromodulation is gaining widespread application as a therapy and also as a research tool. Many of you are familiar with deep brain stimulation. This is a therapy that has had FDA approval for movement disorders since 1997. And there are new generations of deep brain stimulation are being developed and being used in clinical settings for various conditions, in addition to movement disorders such as epilepsy, psychiatric disorders, depression. It also has been widely used as a tool for modulating peripheral nervous system. And there is an area which is very active. It's called bioelectronic medicine. The goal is to control the function of the organ systems by modulating the information pathway from the brain to the organ system via vagus nerve stimulation. So with these systems, there is a need to design a control system. So neuromodulation is basically the function of the nervous system, and like any engineering system, we need to think about control strategy. The first generation of these devices were open loop, and by open loop, that means that the devices, they didn't have any sensing capabilities. And in fact, this is one paradigm and one approach for building neurostimulation. You just deliver certain stimulation parameters and then for a pre-specified amount of time. So the next step was adding the sensing capability and building responsive closed-loop neurostimulation. And this is actually a device that got FDA approval in 2017 for epilepsy, where there was an input, and the input has some detectors, and if there are some events are detected, there are predefined amount of stimulation is delivered. The third approach, which is a more advanced approach for designing closed-loop neurostimulations is adaptive stimulation, or basically you need to have feedback loop where you want to control a certain property at the output of the system by modulating the input and changing the inputs, the stimulation parameters. So there is an ever increasing complexity of neural interface systems, like increasing the parameter space, increasing the number of contacts that the data is being recorded, and also the amount of the information that are collected using neural interface technologies. And it becomes much more challenging to identify optimal stimulation strategies. In addition, controlling nervous system as a complex system we are dealing with a dynamical system that is changing over time, and it requires more advanced strategies. So I will talk about a paradigm in which we can build a little bit more intelligence for these devices. And the idea here is that to allow the device itself learn what is going to be the optimal strategy based on interaction with the brain. And we formulate this as reinforcement learning in the context of artificial intelligence and machine learning, where there is an agent. This agent is representing the control strategy, and it takes some actions. By taking actions, it changes the state of the brain, and depending on the desired output or the desired property that we need from the recordings from the brain, we define a reward for this agent. And through this interaction, this agent, the idea is that to learn to maximize its measure of the reward, and that will basically lead to identifying optimal control strategy in order to optimally modulate the brain. This is a general concept of what we mean by designing intelligence for these closed-loop control systems. So with regard to implementing this paradigm, there are certain elements that are needed, and this can be used in a wide range of applications and neural sensing and neural modulation modalities. And in fact, this is, in addition to being a therapeutic approach, this is a powerful tool to understand the causal mechanisms of controlling certain aspect of neuronal activity and study their the subsequent behavior. So in this approach, what we need is we need to identify a set of biomarkers. Either we do have these biomarkers a priori based on some hypothesis, or we use a data-driven approach to identify those biomarkers from multimodal recording system. And then we will map this into neurostimulation and neuromodulation systems, which could range from electrical stimulation in human to optogenetic in rodents, and electrical stimulation in non-human primates. These are just as an example. And then we learn from these approaches, and we can develop algorithms and use this knowledge in order to build platforms that can facilitate the design of these systems. So in summary, the design elements of AI-based closed-loop neuromodulation will boil down into three main areas. One is identifying target biomarkers and understanding how stimulation affects those biomarkers, designing control system and interactive learning strategies to modulate those biomarkers, and also building, we need to have platforms for design and implementation of such closed-loop systems. Because one thing that is important in this paradigm is the complexity of designing such system, both from prototyping and also from the implementation in experimental and clinical settings. So I will start with one use case on designing automated DBS programming for tremor control, which have collaborated with Svetlana Miasinovich here at Emory. And the goal is to basically build an automated programming system. So when the patients are implanted with DBS leads for Parkinson's disease, after the implantation surgery, they go to the clinic, and a clinician evaluates the patient's response to stimulation and manually adjust the stimulation in order to achieve optimal therapeutic efficacy and minimize side effects. So there was a study back in 2018 that they used wearables, and more specifically here a watch which had accelerometer to record the tremor in an objective fashion from these patients, and use that arm kinematics as an endpoint and target biomarker, if you will, to identify the optimal stimulation parameters. And the strategy that they used was a grid search. So basically, they sampled certain stimulation parameter over a grid, and then they tried to identify which stimulation parameter had the best effect. And the stimulation parameter here contact electrodes and the amplitude of the stimulation on each contact. So we started with data, offline data that was collected to study how different stimulation, how different patients responded to different stimulation. And for this, we used a technique, a function approximation technique, Gaussian process. This is similar to other techniques that you might have been familiar with, for example, linear regression or neural net, and to identify and model how the stimulation affected the end results in different patients. And as you can see here, for different, even for one particular patient, at different stages, the effective stimulation was different. That implies some state dependency in response to stimulation. And also across different patients on the right, there are differences in how the therapy is affected by different stimulation strategies. One advantage of Gaussian process that will give us some level of uncertainty about the regression, and on this here, the surfaces that are above and below the middle surface are showing the upper and lower bounds, and the middle surface represents the mean response of the output. So we use this approach to test a few stimulation control strategies, and we identified that Bayesian optimization was an effective technique to identify the optimal stimulation parameter. And by optimal stimulation parameter here, the surface at the bottom The goal here is that we want to find the bottom of this surface. This is like minimizing a function that is expressed by the stimulation parameter, and this is showing what would be the response to those stimulation parameter. And then the idea is that to find what is the optimal stimulation parameter corresponding to the mean of this surface. So we implemented this from scratch, and in a real-time fashion. We built a system that when a patient comes to the clinic, the system will be able to learn just from interacting with the patient to calculate the target objective function, finds the optimal stimulation parameter, and then tries best to achieve the best setting. And of course, the goal here is that we want to minimize the time that it takes for the optimizer to find these stimulation parameters. And the goal is that we use that as one of the objectives for designing and testing the DBS. So working with old generation of DBS systems, these systems were not designed for such experiments, and we collaborated with Medtronic and group at UW in order to build an interface for these devices, which we could communicate and implement this in a distributed fashion, because the device themselves, they did not have any computing capabilities. So we implemented a workflow for the design of this optimization approach, and with this workflow, basically, we distilled the knowledge of a clinician into an algorithmic workflow. And we tried two strategies, one being using monopolar stimulation and trying to optimize with monopolar stimulation, and provide a decision support tool to the clinician whether they wanted to implement more advanced stimulation strategies such as bipolar stimulation. So the first step to implement such system, we need to make sure that the objective function that we are using to build and optimize the stimulation parameters are representing the desired outcome. Otherwise, whatever results that we are getting will not be meaningful. So we did a regression, a correlation analysis, and we found that the output of the watch, which basically used a classifier to classify the signal from accelerometer into different clinical settings for that represented the outcome, and there was a very good agreement between the clinicians and the output of the classifiers. And then we basically use this Gaussian processes to build models from the interaction with the patient, and this model was built in an iterative fashion, starting from randomly selecting some stimulation parameters, and those were to get an idea of what the stimulation response would be. And then, starting from there, we wanted the optimizer to find the optimal stimulation parameter. We also built safety constraints into the implementation of this system, because one of the issues with regard to using AI systems when they are interacting with the brain is the safety constraints, and this was implemented. The side effects were implemented in the design of the objective function, and we using a safe Bayesian optimization approach, we let the optimizer gradually increase the boundaries of the optimization in order to identify what is going to be the optimal stimulation setting. Of course, the compromise here is that it will take longer for the optimizer to identify the stimulation parameters. And then when we looked at the results across different in our patient population, we found that in general there was a very good agreement with the automated approach, the performance of the automated approach, and what clinicians used to use for programming the device. In both cases, there was significant improvement compared to the baseline, and there was in some cases that the results that we got were better than manual stimulation programming that the clinician used to do in the clinic. So this is one example of implementing an optimizer or a closed-loop control approach to design intelligent closed-loop neuromodulation, if you want to call it intelligence. The other element that I mentioned is that identifying biomarkers, and for the biomarker, we need to find what is representative of the desired outcome that we want from closed loop optimization or closed loop control. And then the other advantage of this pipeline is that it will tell us about what are the underlying mechanisms, and by underlying mechanisms I mean what are the effects on the nerve, what are the neurophysiological effects of stimulation when the closed loop optimizer is interacting with the nervous system. So there was this is another study based on using interpretable machine learning approach to classify between different neuronal states in depressed patient. It was the data that was recorded intraoperatively in patients with depression, and this approach basically there was a baseline recording which is called pre, and then there was a set of stimulation that they were collected, and then there were a set of optimized stimulation, and the goal here was that to see whether the effect of the stimulation on optimal contacts will have different neurophysiological signatures than those which they are not optimized. And by not optimized, they were basically a number of parameters that and contacts that they were tried as a control. So for this, we extracted a set of features, and those features are the canonical frequencies from LFBs that they were recorded, and then we looked at the differences between these signals before and after each of those stimulation approaches, and these basically represented two different brain states that we tried to classify. And then after the classification, we used an feature interpretation or feature learning approach to identify which of those biomarkers had the most impact on separability of these two states. Or in other words, we basically interrogated the classifier to identify what are the most informative features that contributed to this classification. And the approach that we used a logistic regression with elastic net regularization. And the regularization is basically, the idea here is that to sparsify the model and identify the model parameters that are essential for the classification. On top, you can see the cross-validation error as a function of the number of parameters that were present in the model. And as we increase the regularization term, basically it shrank the model parameters. And as you can see, shrinking the model parameters to some degree, up to some point, it improved the performance of the classifier. And then after that, you can see that the error increased, and that shows that those were by further reducing the effect of those model coefficients that corresponds to the input biomarkers, the error increased. So we used the regularization coefficient that corresponded to the minimum cross-validation error, and then we also look at the performance of the classifier, because that is, you want to be able to separate those neuronal states first before interpreting the effects of different inputs to the classifier. And then we identified that in this case, beta, for example, had the most impact on the separation of the states before and after. And then we did this for other stimulation strategies. On the left, as you can see, the mid versus pre, which was a non-optimal stimulation parameter, you can see that there was less separability, which is indicating there was the effect of the stimulation was not significant on changing the biomarkers. So we use this approach in another setting, which we use data from a previous study by Corey Inman. Was published in PNAS, and the study basically focused on the effect of amygdala stimulation on memory performance. And the underlying hypothesis was that since amygdala is responsible in emotional processing, the premise was that if there is some emotional influence on some stimuli, there would be those stimuli would be more likely to be remembered. And they did this study by delivering theta-modulated gamma stimulation by this burst of the stimulation to the amygdala, and then recording from different parts of the brain. This was done in patients with epilepsy, which were in the epilepsy monitoring unit, so their different brain regions were implanted with electrode as part of their clinical intervention. After the stimulation, they did testing immediately, and then one day after the experiment to study the effect on short-term and long-term memory. And we used the same paradigm, but the goal here was twofold. One was to identify what are the signatures of those trials that they were remembered correctly versus those that they were not remembered correctly. That was the first question. And the second question, what was the effect of stimulation If we looked at the stimulated and non-stimulated trial, what biomarkers, what neural features were modulated by the amygdala stimulation, and more specifically, we looked at the downstream effect of amygdala stimulation on the hippocampus. And we basically, I looked into the biomarkers that predicted the correct memories in both CA1 and amygdala stimulation using these approaches. And then we looked at the effect of the stimulation on those biomarkers, and then we tried to see what were the effect of those stimulation were on the neurophysiological recordings in the CA1, and what we found that slow gamma was the most significantly band which were modulated by amygdala stimulation, the slow gamma in the hippocampus. So this is also representing another approach for designing identifying the biomarker that can be used for designing closed-loop neuromodulation in this paradigm. But one thing that is important, especially from a clinical standpoint and also from an experimental standpoint, is that how to design systems that can learn from interaction. And one of the earlier works on reinforcement learning, they were notoriously slow because this is learning based on interaction. And by interaction, this can be considered as a try and error approach. So we started building a platform which could facilitate the design of neurostimulation systems. And this was having people who are the end users of this platform in mind. So the goal here is that to build a number of tools, services, and repositories that can be used for building closed-loop control systems. And as I mentioned earlier, we are using an RL-based approach and also a model predictive control approach for building such systems. The downside of model predictive control, which is established method in classical control, is that you will need to have a detailed model of the environment or the system under control. So we are testing different control design strategies. And as you can imagine, implementing and testing all of these in experimental settings will be very challenging. So we are building simulation environments, which we are leveraging the biophysical and computational models of the brain for interacting with these learning systems to build and prototype them. So this will provide a very efficient way of designing closed-loop control neuromodulation systems. But one of the challenges here is translating these from the simulation environment into the experimental and the clinical setting. And by the challenge, there are two main aspects, is that can the system converge or behave the same way that it is behaving in the simulation environment? And what are the hardware systems that are needed in order to implement these RL-based systems in the experimental settings? So this led to a project that we are building a platform called NeuroWeaver. And the idea in the NeuroWeaver platform is to build some cross-domain closed-loop pipelines for hardware implementation, for implementing these pipelines in the hardware, and also provide a set of models as in a library that can be readily used in designing this system. Here is a simple example of building a closed loop pipeline. And for building a closed loop pipeline, as I mentioned, there are multiple steps are involved. One being the feature extraction. So we need to extract a set of features, do some digital signal processing on the signal. Then there was a step of applying analytics and machine learning in order to extract biomarkers. So these biomarkers the features of the signal can directly be used as biomarkers, or we want to link them to the desired outcome using these analytic approaches. And then we implement those control strategies that I mentioned. And here is a case of using optical stimulation for modulating the brain and electrically recording the brain signals. This is the setup that the in vivo setup that we use for prototyping these systems. But from a design standpoint, why do we need this? And from a clinical standpoint, because as I mentioned, there is no platform that can support building such systems. And the end goal is that we want to build devices and embed these algorithms into chips and devices. And this platform will allow us to create end-to-end pipelines and workflows, which can directly be implemented in hardware for seamless translation into implantable devices or into experimental settings. And for this, we are using FPGA as the target. So for deep learning, as you know, GPUs were essential for implementing deep learning models. It's hard to imagine to train a deep learning model without GPUs these days. And then we are building this system using an FPGA for the reason of being efficient, power efficient, and also translatable in terms of building ASIC chips. So there are several challenges in building such end-to-end pipelines. What kind of an abstraction should we provide for domain-specific accelerators? These are getting into a little bit of details on the computer science aspect of building such platform. But from a user's standpoint, the user wants to have what kind of abstraction should we provide for application programmers. And this is where the people who wants to use this platform in order to build their own pipeline, and how we can incorporate these into an end-to-end platform, because each of those areas that I mentioned in previous slide, those represent a domain specific, and these are domain specific, and designing hardware for those will requires domain specific implementation in hardware. So we are using a full stack approach for building these end-to-end systems that starts with component and flow programming model. This is the development environment, and also adds the compiler and hardware implementation in an end-to-end fashion. So this basically what means from a user standpoint is that we are offering a programming language that will allow express pipelines and algorithms using this programming language, which will be directly implementable on hardware for building chips and for implantable devices. And also we are offering the models, control, stimulation control, biomarker identification, and also feature extraction as libraries that can be used in this environment. And this is an open source platform which we will provide to the community. And this is an ongoing effort that we have on building the platforms. So another aspect of building such system, this system will be on a local machine, but in order to expand the capabilities of these systems, we are developing hybrid cloud infrastructures that will allow distributed implementation of these closed-loop systems. I will talk later about some use cases, which, for example, with COVID constraining all of the interactions that we used to have. Now, with this approach, you might be able to run closed-loop experiments without being in a specific physical lab, and we can use cloud in order to run closed-loop experiments using this approach. And in addition to the distributed nature of these pipelines, we can also make these scalable. There are unlimited, virtually unlimited resources if you want to scale up your the computing, and that can be done in the cloud. So we published a work on software-defined workflows that is basically creates a blueprint for building such hybrid cloud edge infrastructure. Another platform that we are developing here is for Spark program at NIH, and this the goal for the Spark program is to use vagus nerve stimulation in order to develop therapies for various conditions, and the goal here is to regulate the physiology of the organ systems for using vagus nerve stimulation. There are multiple groups are involved, and there are multiple cores are in place in order to facilitate this large consortium. But from a platform design perspective, we are building software infrastructures. That's one of the areas that we are developing. And also we are building physiological models for closed-loop control. As I mentioned, we need to have a prototyping and simulation environment for these devices. So these then fall into models that are built from the experimental data in a data-driven fashion, and also the models that are mechanistic and are based on biophysical equations that predict the organ's physiology to stimulation. And also we are implementing this in the context of closed-loop control for gastrointestinal and cardiac systems. So this is, for the interest of time, I'll just briefly go over these elements, which representing different models and modules that are built in the platform. It has modeling elements, data analytic elements, simulation engines, and also control modules for designing closed-loop VNS control. And the design criteria here is that our goal is that to build a modular environment where these models are containerized, And when the user interact with the platform, basically there are pre-built models that can be pipelined together in order to create a closed loop simulation. And this will allow to combine models from different programming languages. For example, if your physiological model is in Python and your controller is in MATLAB or vice versa, you can build this closed loop simulation. It will be flexible and extensible. It will be compatible with existing platform, and we will target a heterogeneous user base from algorithm and model developers and experimentalists and clinicians. This is the front end of the platform, which basically it's like a drag and drop. You can each of these nodes are representing a physiological model or a controller. And on the back end, this can be implemented both locally, and also it can be implemented in a distributed fashion. In fact, we have our servers in Amazon Web Service cloud services, and then we were able to run closed loop simulation across Atlantic, where the models were running in Switzerland, and we basically ran the controllers here in Atlanta. As far as the physiological modeling is concerned, we are building both mechanistic models and also in silico data-driven models from the experimental setups. Here on the left, you can see a mechanistic model of the cardiac system, which we used for building a model predictive control in order to regulate the mean arterial pressure and heart rate using vagus nerve stimulation. We also used a data-driven approach as a reduced order model, because running this physiological model, detailed physiological model, will be very computationally expensive, and simulating just one cycle of this model may take up to an hour. So we use a data-driven approach to build a reduced order model and approximate this the detailed physiological model. And here you can see on the right, we used an LSTM. This is a deep learning model to predict the output of the model given the input states. And then we used also this for building the architecture of the control system that can learn from interaction directly from interaction with the environment. And also we use this LSTM for our simulations. So here are some of the results that it shows the performance of the LSTM base in controlling the blood pressure, desired levels of blood pressure and heart rate versus the detailed experimental or the biophysical model. We also extended the RL-based approach, and the advantage of the RL-based approach was that the RL agent was able to learn not only the optimal stimulation strategy from interacting with this detailed model, but also it was able to build an underlying model of the system as well. So we used for these experiments, we also used a reduced order model, which in this case we used a temporal convolutional network because it was more computationally efficient as opposed to LSTM. And this is some of the results that we got from the RL-based control approach that started with random states, and then eventually it learned the optimal control strategies in order to achieve the desired level of arterial pressure and heart rate. So in the cardiac system, we had access to the detailed biophysical model, but for the GI, we did not. We only had access to the experimental data. And we have developed a pipeline as part of this platform that used different modalities of data in order to create models from the experimental data. In this case, we used MRI data, fMRI data actually. This was recorded from rats, and it showed the movement of the stomach over time. As you can see, this will give us a very clear view from the spatial standpoint of the stomach, but we had poor temporal resolution. So we are also building models based on the EMG recordings from the electrodes that were placed on the surface of the stomach. And by the way, this data was collected in response to vagus nerve stimulation. In this case, we are recording data from the surface of the stomach and in response to vagus nerve stimulation in order to build models from this time series data and identify control strategies that will induce desired physiological responses in the stomach, and in this case is the coordinated movement of the smooth muscles in the stomach, and we are building the process of building real-time closed-loop control systems for this. So to summarize, precision neuromodulation using AI-based approaches is a promising approach, which I'll consider as the next generation of neuromodulation therapies for neurological and psychiatric disorders. I presented a framework to leverage AI for building such closed-loop neuromodulation control systems. This involved leveraging interpretable AI for biomarker discovery, and also to interpret the behavior of these systems. You can think of them as an autonomous driving system that eventually it's going to learn what is the optimal stimulation approach. But the question is that what does that mean? How we can make these black box approaches a little bit more transparent and use those as scientific tools in order to identify the effects of stimulation on the neurophysiological responses. In silico modeling is an essential and important component of this platform. Either biophysical modeling approaches or data-driven approaches are essential for building more accurate neuromodulation control strategies. And this is going to be an iterative process. So when you collect the data and you build a model, you may not have collected the optimal data or the most relevant data for this task. And through this iterative process, basically, we can improve the data collection and optimize the design of the experiments as well. And last but not least, open source platforms are essentials to create infrastructure for community engagement and also implementing this platform. Because if we build a control system or a pipeline that requires a cluster of GPUs in order to run the computation, this is not going to be clinically useful, and it will be limited in terms of usability in the experimental settings. And to this end, we are leveraging the edge computing as well as the cloud computing approaches in order to address those issues as well. And of course, this was done by the hard work of the people in the lab and also the funding from NIH and other funding sources here at Emory. And this was by no means my own entirely my own work, and this basically was the results of collaboration, multi-center collaboration with many people who I didn't have space to put down all the names here. With that, thank you for the attention, and I'll take any questions.
Applause from the entire virtual audience. Thank you for that very comprehensive talk. There were so many wonderful examples of incorporating new neurotechnology, AI, modern computing approaches into, both the clinical realms and stuff that can advance basic science research. So we have a few minutes for questions, and so the floor is open. Let's see. It looks like there's one question that has appeared in the chat. So Farshad, you can go ahead and unmute yourself and pose the question if you'd like.
Sure. Thank you very much, Dr. Mahmoudi. It was a great talk. So my question is about the variability of the effects for brain stimulation. As far as I know, the effect is highly variable between patients. To what extent your models can be generalized to new population? So basically, I want to ask that, is there a way, or have you thought a way for decreasing the amount of data that we need to train a new model for each patient from our previous experience?
Yes, that is an excellent question. And when we talk about model, that's we are talking about the control model. We are talking about the biomarker model, and we may also talk about the underlying model that predicts the effect of the stimulation. So this variability can also within the same patient will be present. That means that over time the model might change due to the non-stationarity of the system. So in the results that I showed, those were across multiple patients. And for the case of the DBS for PD, we started with random weight parameters for each patient, and the speed of convergence was one of the criteria to optimize in order to reach to a patient-specific response for the therapy. With regard to how we can improve that speed of convergence, so should we always start from a naive state? The question, that probably is not the best strategy. So the question is that how we can leverage prior knowledge from other patients. You can, for example, use patient subtyping in order to start with a blueprint for those patient population, and that could improve the performance. So this is something that we are looking into as to address that patient variation that you mentioned. But this is one example, and that's one of the active areas that we are looking at.
Thank you very much.
I had one question that I wanted to ask. I know that you discussed some of the biomarkers for memory performance and for depression outcomes. My understanding is the biomarkers you're looking at are specific oscillatory frequency bands in some of the data. And I was curious whether your vision is to try to trigger some kind of closed loop stimulation off of a pathological oscillatory band, or more to design a system to reinforce specific therapeutic oscillatory regimes.
So that's exactly. So this is a continuation of this work. This is a collaboration with Washington University and University of Utah that I mentioned, the Corey Inman and John Willey. So we have a project, and the goal here is that to tie the presentation of the stimuli to certain oscillatory state. And even without any intervention, we want to see if we present the stimuli in those states, there is going to be an improvement in the memory performance. And the next step will be to basically try to induce those stimulation, those states via stimulation, to more look into the causal effect of regulating those biomarkers and the subsequent memory performance. This is an ongoing study that we are in the beginning of that.
Wonderful. I know that we're at the time right now. I'm sure that if anyone has any other questions, you can feel free to put them in the chat or unmute yourself. But I did want to thank everyone, for joining us for this seminar, and another round of applause for our wonderful speaker today.
Thank you very much.